Bismillah ar-Rahman ar-Rahim. So as I told you, this is the COE 202, which is basically the digital logic design for the term 202. Okay. This is the syllabus, and I hope that all of you have the prerequisite for the course, which is Physics 102. Okay. This is the information about me. Okay. The best way to contact me is by email. Okay, just send me an email and tell me, for example, that you would like to meet me to discuss something, to discuss homework, or to discuss a subject that you didn't understand. Okay. All right. So office hours are by appointment. You send me an email request, and then just send the proposed time and date, and then I can either reply back by saying, yes, this is fine, we'll meet the same time, or suggest another time that suits me better. Okay. All right. So having said that, okay, we can move on to the course learning outcomes. Okay. In fact, I'll discuss this in a few minutes later. Okay, let's just move on to the textbook. Okay, textbook is this book, which is Introduction to Logic Design by Alan Markovitz. Okay, but you must make sure that you follow our approach. Okay, not the book approach, because the book is not we're not following the exact sequence of topics as listed in the book. So we jump back and forth. Okay. Also, there are some concepts that are not in the book, so you should pay attention to that. Okay. The grading, with respect to the grading, okay, we have 4 components. The first component is Verilog assignments, which is 15%. All right. The second component is quizzes, the online quizzes, 20%. And then midterm and final exam worth of 65%. You must understand that midterm and final exams are common, okay, between all sections. And they will be scheduled by the registrar, as we understood, and they will be physical. So you need to attend the exam physically in order to take the exam, okay, in the campus. All right. Attendance will be taken regularly, okay, and I'm sure that you all know that the 10th unexcused absence results in a DN grade. As a course policy, there will be no makeup for missing a quiz or an exam. However, if you have what we call an excuse, an official excuse for missing that, then I can, waive it for you. Okay, you can just not count it. All right. The rest of the document shows you the topic that we will cover, a rough sketch of the topic that we will cover every week. Okay. I'm not going to go over this now. Before I discuss the course learning outcomes or the course subjects, okay, I would like to take attendance, okay? So all of you, I am going to post a message in the chat, which is a link to Google Forms, okay? I want you to pick your name, okay, in a drop-down list, and then your ID, and then submit. Okay, it shouldn't take 1 minute for all of you. Please, all of you do it. Go ahead. I'm going to shut down the form in 1 minute. Let me stop sharing my screen so that I monitor the progress. Come on, guys. Just 3 responses so far. Okay, 6 responses. 9. In fact, I expect 20 responses. Okay, I have 14, 15. So many students are absent today. I don't know why. If you don't see your name, tell me, okay? And I'll just write your name and ID in the chat area. Tell me that you didn't find your name, okay? And I'll take care of that, okay? We still have 3 more responses to go, and then I'm going to shut down the form. One more. Yeah, so Hassan Al-Marhoon, write down your name and ID in the chat area, okay? And I'll take care of that afterwards, okay? You know what? Let me just add you, okay? So your name should be Hassan Al-Marhoon. Just write down your name and ID, please, so that I can copy it. This is the ID, okay, and your name. You can talk, by the way. Yeah, you know that? Did you know that you can talk? Okay, Hassan, try again. It's the last one. You can find it in the last option. So just do it quickly, please. Let's just get this over with. Yeah, okay. So I'm going to stop it now. All right. So Abdullah Malki, your mic is on. Do you have a question or by mistake? This group is shy, okay? You guys don't talk. So let me reshare my screen with you and open QuickTime. So let me talk about the course subjects, okay? First of all, pay attention, please, because this is very important. It's probably the most important thing that you should hear in the course, okay, in this semester, okay? So the course is called Digital Logic Design, okay? Digital Logic Design, okay? So it's about designing digital logic systems. Not only designing, but also analyzing digital logic systems, okay? And modeling and simulation of digital logic systems. So when we say digital systems, it's in comparison to analog systems, okay? Analog systems like, for example, an analog circuit, okay? So when we want to talk about digital systems, okay, the first thing that we need to establish is to establish the language, the communication between us as a human and digital systems as components or machines, okay? So we as human talk in decimal, so we use decimal numbers, okay? Decimal numbers means the number systems that we are familiar with. Like, for example, when you want to say 107, you write it like this. This is in decimal, okay? However, the computers or digital systems are familiar with what? What number system?
Binary.
Yeah, excellent. They are familiar. They are familiar, or they know binary systems. Okay, or in we abuse the word know. Basically, it's basically we designed them to understand binary system, and binary means two values. Okay, binary means two values, either 0 or a 1. So an example of 12 in decimal, okay, if you want to convert it to binary, it's going to be 1100. Okay, all right. Okay, so we must, in order to master digital systems, we must speak the language of digital systems. The language of digital systems is binary. Okay, so we must be able to express our ideas, the decimal ideas, into binary, and we must understand what the computer is saying by converting the binary to decimal. Okay, so we must be able to go both way, back and forth, from decimal to binary and binary to decimal. Okay, so this is called number system conversion. Okay, so how do we go, for example, if the binary or if the digital system spits out this number here, how do we know what this number is? Okay, we must know how to convert from binary to decimal in order to understand this number. Okay, now you probably have heard of also other systems like octal and hexadecimal. Okay. However, they are basically nothing but a compressed form of binary. Okay. So basically, an octal in octal system, one digit represents 3 binary digits. Okay, and in hexadecimal, one hexadecimal digit represents 4 binary digits. Okay, so this 1100 in binary can be represented with C in hexadecimal. Okay, just C. Okay, and represent that by 16 because this is the base of the number. So this is base 2 and this is base 10, which is the base that we are familiar with. Okay, so the usage of octal and hexadecimal is for our convenience. Okay, instead of writing a binary number that is 32-bit long, okay, you can write it in a compressed form using only 4 hexadecimal digits. Not 4, actually. 4 times 4. No, it's 8 hexadecimal digits. Okay, 8 hexadecimal digits. So whether you so think of whether you want to write a 32-bit number, 32-bit wide, okay, or just 8 digits, hexadecimal digits. So the octal and hexadecimal systems are for our convenience. Okay, so the most 2 important systems are the binary and decimal, and then comes the convenient systems, which are octal and hexadecimal. Other bases, other bases, such as base number 5 and base number 6 and etc. Okay, they are only of theoretical importance. They are really not used. Okay, we just bring them on the quizzes and exams, but in reality they are not used. So the first subject that we should cover in this course, we have to cover, is the number systems. Okay, number systems and conversions. So in order to understand the language of digital systems, we must understand how to convert from a number system to another. Okay, so this is basically the first subject that we should cover. Now, once we understand the number systems, then comes the the usage of these number systems. Okay, so I understood how to do addition in binary, for example. How do I implement a circuit that implements binary addition? Okay, so we will study binary addition here. Okay, addition of binary numbers here. However, we will study the circuits that do addition in this unit here, which is analysis and design of combinational logic circuits. Okay, so this is the second subject that we will cover. Okay, all right, so understanding this is a must to understand this. Okay, so analysis and design of combinational circuits, okay, lets you design the circuits that we studied here. Okay, we will study Boolean algebra and K-maps and stuff like that, just to allow us to implement the concepts that we learned in this unit here. Okay, all right, now for a digital system to be complete, you must have what we call a memory. Okay, a memory, it represents the state of the program of the computer or of the digital system. Let me give you an example of what I mean here. Okay, so now when I say, for example, I'm writing probably a Java program or a C program, whatever. Okay, okay. Now, after completing this code, okay, after completing running this code, what will if contain?
I think it will contain factorial of 6.
Excellent. It's 6 factorial. It's or in general it's n factorial. Okay, where n is 6 in this case. Okay, so now let me tell you this. Let's say that you cannot use variables in programming languages. Can you implement this function, this simple function?
Yes.
You can never use variables.
Without variables, you can't.
You can't. Why? Because of you can change n to some value, for example, 7 here. Okay, but if let's say that your requirement is to compute 6 factorial only, then you can. How can you do that? Basically by multiplying out the numbers in a straightforward manner. Okay, and then outputting this number. That's it. Okay, but if this is a variable, maybe changes. Okay, then you cannot. Okay, you cannot predict, you cannot change the circuit over time. Okay, you have to monitor the variable. Okay, so we call these variables the state of the program. Okay, these are memory elements that are essential for the program to run. Okay, so this is a state and this is another state. Okay, so this evolves over time to be the factorial, and this one here is decremented over time to quit the loop. Okay, so the third objective of this course is to analyze and model or analyze and design sequential circuits, which basically represent the state of digital systems or the memory of digital systems. A computer or a digital system without memory is basically useless. Okay, there are very simple cases like an adder, for example. You can implement an adder without memory. Okay, however, it will be an isolated circuit. Well, what's the point of having an adder floating around without memory, without having it as part of a computer or as part of an algorithm? Okay, so it has to run within the context of memory. Okay, so memory is an essential component that we will study in this course. Okay, and we call memory here sequential circuits. Okay, and we will study analysis and design of sequential circuits as the third component of this course. Okay, however, you must understand this component in order to understand this component. Okay, all right. Now the last component of this course is the modeling and simulation of both combinational and sequential circuits using Verilog hardware description language. And notice here that I have striked through combinational and sequential circuits and replaced them with digital systems, because digital systems are either combinational or sequential. Combinational is a digital circuit that contains no memory. Okay, for example, a circuit that receives A and B, okay, as binary numbers and outputs A plus B. That doesn't require a memory. Okay, it doesn't require a memory. I'll tell you from now, it doesn't require memory. But a circuit like, for example, the algorithm that we mentioned, okay, does require an algorithm. Okay, does require a memory. Okay, does require a memory. So a digital system can be either combinational, like this circuit, or sequential, or a combination of both sequential and combinational circuits. So one of the objectives of the course is to learn how to model and simulate digital systems using Verilog HDL. So the first Verilog module that we will cover is during this component here. Okay, and the second Verilog presentation will be right after completing the analysis and design of combinational circuits. And the third one is at the end of sequential circuits. So the Verilog part of the course is going to be intermixed with the content. Okay. All right. This is about the course. So if somebody asks you, what do they teach you in digital design? What would you say? Okay, it's just 4 components, 4 things: number systems, analysis and design of combinational circuits, analysis and design of sequential circuits, simulation and modeling of Verilog of digital systems using Verilog hardware description language. That's it. Only 4 components. It's as easy as that. Okay. However, the devil is in the details. Okay, the course has so many parts, and just to warn you, okay, the first part of the course is easy. Okay, it's always easy. Okay, and people can get probably full mark in the first 2 chapters or 3 chapters of the course. Okay, however, when it comes to the rest of the course, people screw up. Too many people screw up. Okay, so part of the reason, I believe, it's not because the course is difficult, no, but because students probably think that all of the course is as easy as the beginning, so they just procrastinate reviewing. Okay, and then when the exam comes, they see that they have to catch up so much material. Okay. So my advice to you is to review day by day, okay? And do not say this is simple. No, always try to create problems yourself and solve them, okay? And make sure do a sanity check to check whether your answer is correct or not. Okay, and you can always come back to me for this. Okay, any question about that? Any question? Okay, so let's move on now to discussing digital systems versus analog systems. Okay, so let me erase this, okay, and ask you now, when I say an analog signal or a digital signal, did any one of you is any one of you taking the circuits course?
Circuit analysis.
The 202, I think. Yeah.
Yes, I took it.
I can barely hear you. By the way, your voice is far away.
I took it. Yes, I took it.
Okay, so you took it already.
Yes.
Okay, so you do remember. So you can tell us, for example, an example of an analog signal, right?
Actually, we didn't study analog signals, and it's introductory of the course.
You are taking it this semester, you mean?
No, actually, I took it, but we didn't study analog signals.
No, you did study analog signals. It's an important subject of the course. Analog signals means, like, for example, let me give you an example: voltage,
Temperature.
yeah, temperature,
Okay.
and current,
Yes.
force. Okay, anything, any physical quantity. Okay, physical quantity can be thought of as an analog signal. Okay, a signal doesn't have to be, by the way, a signal doesn't have to be input through a wire. Okay, a signal means it's a function of time. Okay, it's a function of time. So so how do we define analog signals? They are continuous function of times. This is the main definition of analog signals. They are continuous function of times. Digital signals, on the other hand, they are what we call piecewise. How do I write piecewise? I hope my piecewise continuous functions that change during. This is criteria number 1, and criteria number 2: changes at fixed points of time. Okay, so you cannot change it. For example, it changes every 1 second. At time equals 1, 2, 3. You cannot change the signal during 0.5, for example. Okay, and it is a piecewise continuous. Okay, and also the third one. Okay, third one is that it is quantized. Okay, quantized mean, okay, it means what? It means that it has a limited or finite number of levels. Okay, finite number of levels. For example, when you say, well, a temperature ranges between for example 20 to 25. However, it is a real variable. Okay, a real variable that has infinitely many values. Okay, you cannot just say you're only limited by the representation of the real value. Okay, but it's a continuous function of time, so it can take any value in between. So there are infinitely many values between 20 and 25, or even between 20 and 21. Okay, degrees Celsius. Okay, So just taking a small period of time or period of temperature, okay? Just taking a small range of temperature, okay? You can always find an infinitely many values inside of it. However, when you quantize it, when you say, well, I will not have infinitely many values, I'll have finite values, okay? So I'll have only 21, 22, 23, and 24, okay? That's it, only 4 values in between. I will not have 20 or 25, and not the values in between, okay? So this is called quantization. So you are quantizing the levels of the signal, okay? So when you're for example, when your actual signal, when your actual analog signal is 23.5 or 23 point, let's say 25, okay? Then you just round it to the nearest level, which is, for example, 20, for example, if it is 21.25, then the nearest level is 21, okay? So 3 characteristics of digital systems: piecewise, continuous, okay? Actually, it's 2. If you do these 2, okay, if you guarantee these 2 requirements, then it is automatically going to be piecewise continuous, okay? So it changes at fixed points of time, and it is quantized. Let's take an example, okay? Let me just erase this. This is for the section before you. And rewrite this from the beginning. Okay. So let's say that we have a signal, okay, which is basically a voltage signal, and we would like to generate or to fabricate a digital voltage signal, okay? So in order to be able to do that, okay, first of all, I must use quantization, okay? Quantization means that I have to have a finite number of levels, okay? So I'm going to have 4 levels here: level 0, level 1, level 2, and level 3, okay? So let us say, for example, I have this signal, which is an analog signal. Okay, this is an analog signal. Okay, it is continuous, and it is having a continuous values. Okay, however, for the let's say to generate a digital version of this signal, okay, we look at every sampling point, which is, for example, starts with a 0 here. Okay, now let's use a different color. Now at 0, the closest quantization level is 0. Okay, so the signal, the digital signal, the digital version of this red signal is going to be 0 until the next sampling point. Okay, at the next sampling point, we check the value of the signal. The value of the signal here, okay, and discover that the value is closest to level 2. Okay, so my digital signal will go to level 2 now. Okay, and it will stay at level 2 until the next sampling point. At the next sampling point, okay, I check the value of the signal and discover that it is closest to where? To 2. So I do not change, the signal doesn't change value until level 3, until time 3, okay? And at time 3, I check the value of the signal. What is the value here? It's exactly 1, Okay, so this is going to back to level 1. Okay, I made a mistake here. I made a mistake. Sorry about that. Oh man, I didn't go to the right level. Okay, so the level should be here. Okay, this is the level, right? Until 2. Okay, and then here I check the value of the signal, and it is still 2, so I keep going. I keep the value 2, and then here, what is the value here? I said it's 1. Okay, so I go back to 1. All right, and then I keep at 1 until 4. Okay, and then at 4 I check the signal. Okay, and then this one here is level 2. Okay, not right over my signal. Okay, this is level 2, so I go back to level 2. All right, and until 5 here. Okay, at 5, who can tell me what is the level at 5 at time equal 5?
1.
What is that?
1, 1.
1.
1. Excellent. Yeah. And then I keep at 1 until the next sampling point. So if you see the pink signal here is a digital signal, a digitized version of the red analog signal. Okay, you can see that it really resembles some of the characteristics of the analog signal. However, in order to make it accurate, in order to make it more accurate, okay, you'll have to reduce both the sampling or increase the sampling rate or reduce the sampling period, okay, and increase the quantization levels. So for example, you quantize every quarter, for example, instead of every 1. Okay. However, just the purpose here is just to show you how to generate a digital signal out of an analog signal. All right. Any question?
Doctor.
Yeah.
When the sample is exactly at the middle.
Yeah, I mean, okay, this is an excellent question. Okay, it's going to be there is going to be what we call a forbidden region between the signals. Okay, just to guarantee that there is no overlap. Okay, this is details. Okay, we don't worry about the details too much. Okay, however, if even if you do that and then the signal is exactly there, okay, then you have to choose which one. You have to choose. All right. Usually the comparator, we use what we call an analog comparator, which goes by this symbol here, analog comparator, which produces either a 1 or a 0. Okay, that tells us whether the positive terminal is greater than the negative terminal or not. Okay. It doesn't tell us the equality. Okay, so we don't care about the equality. All right, so whichever is greater will take over, or whichever is lower will take over, whatever your design is. But we don't care about this. It's not the purpose of our course. I'm just introducing to you the concept of digital signals. Okay. All right. So the most important what we call digital signal out there for us is what we call binary signals or binary digital signals. Okay, so binary, it means that it has 2 quantization levels. Okay, either level 0 or level 1. Okay, so here you can see that level 0, the center of level 0 is here. Okay, we use the same color as, okay, You can see that this is the center of level 0, and this is the center of level 1. The center of level 0 is 1.25 volts, and the center of level 1 is 3.75 volts. So the voltage swing, okay, goes between 0 and 5 volts, okay? So in between, there is a forbidden area here, okay? If your signal, okay, by mistake goes in between, then you have an error, okay? So here we have a signal called x of t here, for example, let's call it x of t, all right? That goes 1, then 0, then 1, then 1, then 0, then 1, okay? So we would like to sketch the signal on the plot, okay? So it's already sketched here. I'm going to resketch it for you using a different color, okay? Using a dark green, for example. Okay, so the 1 here, okay, is here. Okay, so this is the 1. Okay, so we assume that we are taking samples every 1 second, okay? So it is going to remain at 1 until the next sampling point, which is here, okay? And then we get a 0. So we go to 0. Do you see that? Then we stay at 0 until the next sampling point, which is 2. And then we have 2 1s here, okay? 1 followed by 1. So we go to 1 here, and then we go to 1 again. And then at 3 as well, we go to 1. Okay, we remain at 1. Are you following?
Yes.
Yes.
Okay, and then we go to 0 and then 1. So this is 0. Okay, until 5, and then 1. All right, so this pulse train, okay, is equivalent to 1 0 1 1 0 1, which is nothing but our digital signal here. Okay. So basically, in digital design, okay, in digital systems, we don't worry about the voltage too much. Okay, the voltage changes according to the technology. Okay, what we care about is the level of the signal, whether it's level 0 or level 1. Okay, and we call these levels logic 0 and logic 1. This is by convention. Okay, you can flip them if you want, but all the world have agreed that the bottom part here is logic 0 and the top part here is logic 1. Okay, so the signal here is 1 here, and then 0 here, and then 1, and then 1, and then 0, and then 1. Okay, so I want you to differentiate between the concept of logic 0 and logic 1 and the voltages. Okay, the signal voltage is 3.75 when it is logic 1, for example, or let's say the voltage ranges between 2.5 up to 5, okay, when it is logic 1, and when it is logic 0, the voltage ranges between 0 and 1. Okay, so this is like a conceptual thing. Okay, in addition to the fact that the signal, okay, does not really in reality does not really resembles a straight line. It has some noise. Okay, there is some noise and there is a fluctuation, and we need to make sure that the fluctuations are within the what we call the noise margin. Okay, the noise margin is up to here. Okay, let me just make sure that I get the noise margin correct, because the forbidden region is not part of the noise margin for logic 1 and the noise margin of logic 0. Okay, so as long as these fluctuations are within logic 1 or within logic 0, we are fine. But if the fluctuation is too much, okay, then we are in big trouble. Okay, because we cannot differentiate between logic 0 and logic 1. Okay, so I guess I'll stop here. Okay, and check if you have any questions. Guys, do you have any question? Okay, in the next lecture, we will start, inshallah, binary systems. Okay. So we will start this unit here. Okay. The next lecture, we will start this component of the course. Okay. So any question about the course in general? Or the syllabus or the exams or the grading or something. I want you to talk, basically. Okay.
Yes, Doctor.
Mhm.
How would the question on what we just studied appear on a quiz, for example, or homework?
For this material here, it's an introductory
Yes.
material. Okay. So most likely you will not have questions about it. Okay. But starting from the next lecture, we will start the binary systems. And then the best advice that I give you is to look at old exams. Okay. Look at old exams. They're available. And sometimes there are errors in the exam solutions. Okay. Due to posting an older version of the solution. Okay. But I trust you guys that you will solve it yourself and discover these errors yourself. Okay.
Okay. Thank you.
Yeah. By this, I am done. Okay. If you have any questions, you can stay. Otherwise, you're free to leave. I'll see you next lecture.
Thank you, Doctor.
حياكم الله.
There is a question in the chat.
There is a
From-
question in the chat. Let's see. يعني يا شباب يا ليت ما تستخدمون الشات لأنه it's very there is no alert or something. So do we have to download a certain software for Verilog? The answer is no. This is a good question. We will be using what we call the cloud for the simulation and the modeling, which is basically called the EDA Playground. Okay, there is a website called EDA Playground. Okay, so you'll be using that. Okay, and I advise you to go there and explore and create an account at least to start with. Okay. The website is called EDA Playground. Okay, I'm writing it on the chat. Yeah, fine, no problem. Just the problem is that I don't see the chat right away. Okay. Yeah. Okay. I guess there are no questions. Yeah, let me stop recording and sharing.